Hi, welcome to another lecture on PLCs programming. So today we will see on basic switching applications. So how to solve simple logics in using a ladder logic. So today I have taken two examples. So let's look into the first example. Now, here is my first example. So this is just a Boolean expression, right? In my previous lecture, we discussed how to convert a Boolean expression into ladder logic. So here I have taken a simple Boolean expression, and I'll show you how to convert this Boolean expression into a ladder logic. So now before I start, for any, whenever you face this kind of questions or a problem, there is a one simple technique which already I explained in my last lecture, my previous lecture in the ladder logic. So here was simple things like, if you remember the four things like, now, in any Boolean expression, if you observe, there will be in the two standard forms, either in POS, product of sums, or in a SOP, sum of products. So now usually in any of the form, whether it is a POS or SOP, here normally we used to find basic some literals, right? So here here A, B complement, and C complement, right? So a normal literal with a complement literal, and in between these literals there are two operations, that is AND operation or operation usually, right? So now when you want to convert this into the Boolean expression, simple. Whenever you find a simple literal like a normal, like say for example A, then you have to replace that with a normally open instruction. Similarly, whenever you find a literal with a complement, then simply replace that with the normally closed instruction. And then now in between these two literals there is a AND operation, that is a dot operation. So whenever there is a dot operation, then put these two instruction in series, put them in a series combination. Suppose if there is a literal like this, A plus B bar, now the operation between these two literals is a plus. Okay, so whenever you see a plus operation, then put them in a parallel. Okay, that's it. So if you can remember these four things, then you can convert any Boolean expression into the ladder logic. Okay, so now let's look into the expression. We will solve this problem now. So here the first thing is A, B complement, C complement, that is Q1 is the output. Okay, let's solve this. Now first of all, A, as I said, it is without a complement, so we can use a so let me draw a rail of my ladder logic. So I used it a normally open instruction, and I have addressed a A, right? Next there is a B complement, and you see that there is a dot operation between A and B. So now this time I'll use a normally closed, and I have to label it as B. Don't put the complement on the address, because this is just an address, and this instruction is already representing in its inverted form, that is in complement form. Okay, it's normally closed instruction. Then another literal, that is a C, now again with the normally closed. Why? Because there is a complement over here, so this is a C. Okay, now finally, now this is a combination of my inputs. So total in this expression there are three inputs, A, B and C. A in its normally open form, B and C in its normally closed form. Why? Because there is a complement for these two literals. So this becomes the ladder logic for the given expression. So finally this is the output of the Q1. Okay, so this Q1 will follow the logic A dot B complement dot C complement. Clear? Similarly, now the next expression here we have is A complement B C complement, that is Q2. Okay, now in this expression, again this is also a product term. So here A complement, again three inputs, A, B, C, right? So let's put them in the ladder logic form. So A in its complement form, in series, B which is in normally open. Why? Because there is no complement here, right? B here, and then in series with C complement. So this is a C and followed by Q2. So now the Q2 follows the logic, that is A complement, B, C complement. Okay. Now finally, in the last expression, A complement, B complement, C, that is Q3. Okay. Now this is also a product term. So here A complement, B complement, and finally C without a complement. So normally open instruction followed by a Q3. Okay, so this is how we can develop the ladder logic programming for any given Boolean expression. So suppose if the same is in the form of a let's say in a sum term, then I'll convert this as into the sum term. Let's say suppose if it is A complement plus B complement plus C. Okay, now this is just an example, has nothing to do with the logic. So if this is a term, then how to draw the ladder logic for this? Same rule applicable. So A is in complement form, so which means A is normally closed. Okay, now the next term, the B complement, it is not dot with the A bar, so it's a plus operator. So plus operator means parallel. So I have to take the new branch. So this time again, this is for B. Okay, this is for a B. Then similarly, there is another input again with a plus operation. So I need to take one more branch, that is for C. Now all these branches are parallel, so I have to close these branches, and finally here is the output. Okay, so if this is a Q4, then this is my output. Okay, so this is how we can convert a product term or a sum term or any standard Boolean expression, whether it is in SOP or in a POS, into the ladder logic. Okay, now I hope you understood this example, and then when you understand this logic, any combination you have in a digital logic, there is a combinational designs. Okay, there is a combinational designs, so you can design any kind of a circuit in the ladder logic. So one thing you need to understand first is for any design, the basic rule is you need to understand the number of inputs and outputs. So how many inputs are required for the logic design, and then how many outputs involved in the particular process. So say for example, there is an application where I have two inputs. Okay, I have two inputs, and then output I figured out as only one. Okay, now when I figure out this inputs and output in any application, the next thing, important thing, what you can do is you need to try to draw the truth table. Okay, try to draw a truth table among this combination. So here I have two inputs, so maximum possible combinations are 4. So 0 0 0 1 1 0 and 1 1. Okay, so in this way we can able to design any kind of a Boolean expression into ladder logic. So you know that in digital electronics there are several combinational designs available. So for any design, the basic key is first thing is you need to estimate the number of inputs required for the logic, Similarly, the number of outputs also, right? So let's say for example AND. In AND, you know that basically universally standard it needs two inputs and one output, right? Similarly, if you take a half adder, in a half adder there are two inputs and the two outputs, sum and carry, right? So in the same way, when you are designing some logic, so how many inputs and how many outputs required, so that you need to estimate. Okay, so once you figure out this inputs and output, the next thing is you need to form a truth table. So let's say I have two inputs x and y and one output q. So you need to figure out the table. So hence two inputs, so maximum possible combinations are 4. So 0 0 0 1 1 0 and 1 1. Okay, so these are the maximum possible combinations. So now for this combination, how you want your logic to respond. Okay, say for example I want to respond like for 0 0 0 and 0 1 1 and 1 0 1, and similarly for 1 1 I don't want any output, I want a 0, right? Now this resembles a logic, a very popular logic, yes, that is XOR. Okay, XOR. Okay, and you know that XOR expression, so this x y complement plus x complement y, so this is a Boolean expression. Okay, and for this Boolean expression you got a output, right? Now suppose you have some different application like three inputs and one output, then just list out all your combinations and then list out your requirement. So what is the output you wanted, and then from this output how to get the Boolean expression. You know, in digital logic the Boolean there is a standard method called K-map, Karnaugh map, we call it as Karnaugh map. So by using this Karnaugh map, so you can draw the map, you can make the groupings, and from the groupings finally you can able to extract a Boolean expression from the logic. Understood? Once you get the Boolean expression, that's it, you can good to go. You can convert this Boolean expression into the ladder logic. So this is an just an idea that I'm giving you, that you can able to create any combinational design in a ladder logic. Understood? So in the combinational designs there are decoders, encoders, multiplexers, demultiplexers, and so on, many more. Okay, so with this I hope you understood how to design a logic and given a Boolean expression into the ladder logic. Clear? Now let's move on to the another example. So here again one more interesting example in the switching application. Why I'm calling the switching? Why? Because in here when you look at my previous example, here the inputs and the outputs, it's just a binary numbers, right? If any input is changed, if it change its status, it means if it switches from 0 to 1 or 1 to 0, immediately the output has to respond. The output also will respond in the same way like 0 or 1. So overall here what happens is input and the output will just switch its state from low to high or high to low. So that's why I call them as a switching application. Similarly, in PLC, we have a sequential application as well. What happens in the sequential application? In the sequential applications, there will be some timing. Okay, so you can schedule, you can delay the output, you can bring some time parameter into the logic. Okay, so but here in the switching application there is no time parameter. Instantly, whenever the input changes, instantly the output will change. Understood? Let's look into this two-way switch. First of all, we'll try to understand what is a two-way switch. So in two-way switch application, there are two switches, switch 1 and switch 2. Okay, so just for an example I have taken in series, but in real time it is not in series. All right, so the two switches followed by an output, that is a lamp, let's say the lamp. Okay, now the concept is very simple. Now by using any of these switches you can turn on or you can turn off this particular lamp. Understood? So that is a main concept of two-way switch. Now where we apply this two-way switch, I'll give you one example. Let's say there is an multi-story building. So let's have, there is a ground floor and the first floor. Okay, and in between the ground floor and first floor there is a staircase. Okay, and similarly here. Okay, now there is a lamp over here. Okay, there is a lamp over here, and Now, a person who is taking a staircase from the ground floor to the first floor, or the vice versa from first floor to the ground floor, he has to make use of this. He want to turn on this lamp, and for that there are two provisions for him. The first one is, suppose if the person is in the ground floor, there is a switch in the ground floor. Okay, this is switch 1, and suppose if the person is in the first floor, and if you want to turn on, there is a switch provision in the first floor as well. So overall, what I mean to say is, there are two inputs, which means the two switches, and there is only one output. So a user can able to switch this lamp from any of these two switches. Okay, now the simple thing, suppose if the person is in ground floor, he definitely make use of switch 1, and he will go to the and he'll make use of the staircase, and once he reaches to the first floor, again he can make use of this switch 2 to turn off this particular lamp. That's case 1. Case 2, say for example, if he is in the first floor, and he can make use of this switch 2 to turn on the lamp, and after taking the stair, then he can use the switch 1 to turn off the lamp. So in this case, these two switches can be used to turn on or turn off. Understood? Now, how to design the logic for this? Same, like I said previously, for any design, first you need to estimate the number of inputs and the output. So in my case here, there are two inputs and one output. Okay, so what next? Bring the truth table. Try to form a truth table. Switch 1 versus switch 2 versus my lamp. Now the truth table. So possible combinations, only two switches, so possible combinations are 4, 0, 1, 1, 0, 1, 1. Okay. So now after these combinations, now you can decide the output. Okay. So now for 0, 0, I want the lamp to be on. I want the lamp to be turned on. Okay. Why? I'll tell you. In 0, 1, which means one of the switches responded, which means already the lamp was in on. So what happens now? It becomes closed. It becomes off, because now in this case, now initially the lamp is on. Now somebody has switched this switch 2. It means a person has taken the staircases and he pressed the switch. So what happens? The lamp will turn off. Understood? Similarly, next, coming to the 1, 0 combination, here also what I want is the lamp to be turned off. Same is the case. A person from first floor, then he is going to the ground floor. After taking the staircase, he switched this switch 1. So he pressed the switch 1 and it is turned on, and again it is turning off the lamp. Understood? Next thing is, in 1, 1 combination, again I want the lamp to be turned on. So why I have taken the this condition, you'll understand soon. Okay, so now this is my truth table. The design is ready. Okay, means with the input versus output, the truth table is ready. So I call this as truth table. Okay, so first rule is you need to identify the number of inputs and output. The second thing is you need to figure out the input and you need to figure out the truth table. So after that, now when you look at this logic, what is the popular gate which comes to our mind? Yes, that is, yes, XNOR. Okay, this combination, it represents the XNOR logic, right? So and how the XNOR logic is? The XNOR logic is very simple. So for a given output, the XNOR logic is A into B plus A bar B bar. So this is a Boolean expression for XNOR. Okay. Now let's once we get this Boolean expression, and we can easily convert that Boolean expression into the ladder logic. So now let's look into the ladder logic for the this given Boolean expression. So now we got this Boolean expression. Let's convert this into the ladder logic. Now here is a expression. Q is equal to A into B plus A bar B bar. Okay. Now when we realize this into the ladder logic, so there are only two literals, A, which I'll take as a normally open, and B again in series. Why? Because there is a dot operation. So in series, again here it is a normally open because there is no complement over here, right? Next, parallel, because plus parallel, another term, that is A complement, don't put the bar here, series with B. Okay, now these two are part of the logic, so followed by the output. This is our Q, and Q is nothing but our lamp, and here A is nothing but switch 1, B is nothing but switch 2, and Q is nothing but the lamp. Okay, now let's figure out this logic. We decode this logic, how whether it works or not. Okay, now as we have considered the logic, so this is our staircase. So here there is a switch A, and here is a switch B, and here is our lamp, that is a Q. Okay, right. Now first of all, we'll take case 1, means the person from ground floor to first floor. So now what happens is, now the lamp is right, currently he has not switched any of this lamp. So now what happens, A is 0, he has not pressed any switch, so A is 0, and B is also 0. Okay, first case, A, B, okay, and our output, A is 0, B is also 0. He has not pressed any switch. Now what is the condition? When A is 0, B is 0, the lamp will be in on condition. Yes, lamp is on condition. So without pressing this switch, he can take the staircase and he can go to the first floor. And after reaching the first floor, what he will do? He will press the B switch. So he will go to the first floor and he will press the B switch. So now what happens? The moment when he press the B switch, as per our logic, the light will be turned off. The light will be turned off. Okay, so this solves the case 1. Okay, now coming to the case 2, the person from first floor, he want to go to the ground floor. Okay, now what is the condition for him? Now the current state of this lamp is off. It is in off. Understood? So what he will do first, he will switch on the lamp. He will make use of this nearby switch, that is B, and he will turn on this B, and then he will move on to the next phase, right? So what he will do now, previously it was in one condition, right? Because in case 1, the switch was become 0 to high, right? Now in case 2, what happened? This guy will convert this high switch to low. Okay, so he will make this as low. Okay, he will make this as low, and already A is on low condition. So again this 0 condition, which means it is almost similar to the previous, right? Now what happens? Now the lamp will be turned high, so it will be turned on. Now he will take the staircase and he will come to the first floor, and once he reach to the first floor, what he will do now? He will turn on this switch A. You will turn on the switch A. So what happens when switch A is turned on and B is already in 0? So here what happens? The output will be off. Understood? So with this, the logic can be utilized. This XNOR logic can be used for this two-way switch. So with this example, I have shown you this demonstration of the two-way switch for the staircase. So here is the logic, and how I have designed this logic with the help of the truth table. I have shown you clearly in detail. Okay, I hope you understood this two-way switching, and we'll see more examples in my next video. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.